So just like electron configuration described where electrons were located, orbital box diagrams are going to be a way of drawing a picture to show where electrons are located. So what we're going to do, you're going to draw boxes to represent the first shell, the second shell, the third shell. You're going to draw the right number of boxes for the S and the P, and those boxes are going to be what you're going to fill in with an electron. So you want to go from lowest to highest. You want to draw your boxes from the first energy level on up. And we're going to fill those from lowest to highest because that's Auf Bau's principle, so a new vocabulary word. Write it down because this one comes up and you'll be asked which one of these violates Auf Bau. Well, Auf Bau says that you're going to put electrons on the first shell first. It makes sense because the first shell is the closest to the nucleus. That's where electrons would have the most desire to be because they're negative, they're attracted to the positive nucleus. So we fill from the first shell. Once the first shell is full, then we fill the second and third. So to remember which rule is each rule, we would say abajo for bottom. So Auf Bau is telling you to start abajo if you want. Okay, then we have Hund's rule. When we're filling in our boxes, you guys are going to see that if you have boxes that are equal energy levels, for example, if you have the 3p orbitals on the p subshell, you're going to split before you pair. So first you put one electron in each box, and then you start to pair those electrons. And the way you can remember, the reason that's going to happen is that electrons are negative. So if an electron is just as likely to go in one orbital box as it is the other because they're the same energy level, they're the same, we'll say, distance from the nucleus, then they're going to spread out first because all electrons are negative. There's that electron-electron negative-negative repulsion. So spread your electrons out, and then you start to pair because there's no other space at that energy level. That's called Hund's rule. And the way I remember that, just to get the rule straight, because you have to say like which one of these violates Hund's rule. Which one was Hund's? Hund's is split before filling, just like I would think like divide and conquer. And the only reason I think divide and conquer is going to be from Attila the Hun, not the Hund, but Attila the Hun. So that works for me. Pauli exclusion, well that's the one I don't have anything to remember, but that's okay because it's the third one. Pauli exclusion tells us that we can have 2 electrons maximum paired per box. Okay, yeah, you're not gonna, it's just how many fit. Any more than that, they don't fit. They're not stable, they repel each other too much, there's not enough space, so that's just a rule. Okay, let's go ahead and draw one of these. Let's first write the electron configuration for oxygen. So oxygen, first I'll fill in the first period. So in the first period, there's the S subshell. I put in 2 electrons. And let's see, then I'm on the second energy level or the second period. And I'm in the S subshell again, and there's 2 boxes. I put in 2 electrons. And then I'm in the P, so I'm still in the second energy level, P subshell. And to get up to oxygen, oxygen is the 4th one over because it has a total of 8 electrons. So I'm just going to put 4. That's the electron configuration for oxygen. The orbital box diagram is, first I draw, this is going to represent 1, first period. It's my S's, they're at the bottom of my drawing. Then next I'm going to represent the second energy level. 1 box, because I'm talking about 2s. And then I'm going to go up a little bit. 2s and 2p are very close to each other, but the s is just a little bit more stable. So I want to draw some boxes representing the 2p. I'll make them a little bit higher, but I'm going to put them over here. And P subshell has 3 orbitals. So I'm going to draw 3 boxes. And I'm making them big by accident. I'm just not good at drawing. So then I go ahead and I start to fill these in. Abajo, hasta arriba, because I'm going to bottom to top, because Auf Bau tells me. So I'm going to put 2 electrons here. I'm going to face 1 up and 1 down. That designation is just saying they have opposite spin. So we say electrons have opposite spin because their charges kind of cancel each other out in ferromagnetic metals, which we'll see. So just make sure you put 1 up, 1 going down to represent that they're traveling in a different way. Then, okay, this is full. So now I have to go up. I'm going to put 1 up, 1 down. Hund's hasn't applied yet because I don't have any boxes of equal energy. So I filled these guys down to 2p. I have 4 electrons. This is where Hund's tells me I want to go single, 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 1, 2, 3. I need 4. Now I pair. So you wouldn't want to have 2 here and 2 here. That would be violating Hund's rule. if I put 2 in this box and 2 in this box, because there's another open energy level that's not being occupied at all. And these electrons are all negative. They want to split. They want to spread out as much as possible. So that's orbital box. Do I give you? Yeah. Keep watching if you want to practice for an orbital box. So let's go ahead and we'll go ahead and write the orbital box diagram for. How about magnesium? So here's magnesium. It's really good. Go ahead and hit pause if you want to try this and then see if you can do it. So hit pause and draw the orbital box diagram for magnesium, or the electron configuration first, and then the orbital box diagram. So pause if you want. So the electron configuration is on the first shell, there's 2 electrons. Second shell, S subshell, there's 2 electrons. Still in the second shell, but now you're in the P region, there's 6. Now you filled up the second shell. I'm just looking on the periodic table because I looked at it so much. It's right over there for me. Now I'm on the third shell. I'm in the S region first. And actually that's magnesium. Magnesium has 12 electrons, and I've got 2, 4, 10, 12. So my 12 electrons. So I'm going to have 1 box for the first shell. And then I'll go S. Really, like I told you, that's crazy. I can't draw a straight line. Okay, so there's my 1s, there's my 2s, oops, 2s. Here's my 2p and 3s. So I'll jump up. Okay, and I'm going to put 2, 2, and 6, so I go up and then down, putting 2 per box because that's the max that'll fit, Pauli Exclusion principle. I'll put 1 per box, but since this thing gets filled up, it can't violate Hund's anyways. And bottom to top, following off bow. Done. Looks like that. One thing you can use this for is if you want to know what electrons, like what charge does this form, the easiest way for this thing to have a full S and P is if it loses these 2. So we know that when magnesium, oops, I said 3P, that's a 3S. When magnesium forms an ion, it loses 2 electrons from the 3s. That's it. Quite often you get asked which one of these violates a rule. So let me give you some examples of things that violate rules, and you try to figure out which one is violating each rule. And also tell you which could happen, which couldn't. So this will be, I want to go S and then P. So here's 1s, 2s, and then 2p. And we'll just draw 3 things. So this first one, let me know which one you think this is violating. And we'll leave it like that. Then, actually, look at this. Then for the next one, it'll still be 1s here, 2s, and 2p. I'll make this violate a rule too. Okay, and then this one will violate a rule as well. So see if you can figure out which one each one is violating. So for this first one, we know we're supposed to fill from the bottom to the top. We didn't fill this. So this violated off bow. Then for this one, I can see these are not paired. Pauli Exclusion says you can have a max of 2 paired electrons. I have 2, but they're not paired. So this is violating the Pauli Exclusion principle. And then for this one, filling bottom to top, I have paired per box. But I didn't split before I started to pair, so that violated Hund's rule. Another way you could violate Pauli is if you put 3 electrons in a box. These will never happen. This one does, because you can excite electrons. If you remember from your Gen Chem class, or we'll light some metal solutions on fire for you guys so you can see this. You can excite electrons from a lower energy level to a higher, and then when they fall back down, they're losing energy. They give off that energy in the form of light. So that's how your sodium lamp works, or neon lights. And that's it for orbitals, orbital box.